Hello, welcome to lecture number 28. In the previous lecture, we saw the similarity between planetary Rossby waves and topographic waves and the reason why they exist, that is, they have to conserve the potential vorticity. And these are all based on inviscid systems. Now, having discussed these barotropic systems, barotropic waves, we now move to a system which is baroclinic in the sense that there is now the vertical structure um, of the ocean or the atmosphere is important here, and that leads to generation of some kind of disturbances, which is pretty interesting in its own right. So we will study the formation and generation and the properties of a certain class of waves which are called internal waves. So as the name suggests, the internal waves are internal to the system, whether be it atmosphere or ocean, and these are something that we may not readily appreciate very easily because of the fact that we don't see them. Similar to the surface waves, some of us, we have seen the ocean or a river or a pond, or even seen it in movies. We know that waves are mostly seen on the surface because that's where we live. We live on the coast and we can see the waves. But there are waves, the disturbances which are happening, which are being created regularly, destroyed, and they are propagating inside the ocean. And we will show the properties of these internal ocean and see how, I mean, why are they, I mean, the reasons for their existence and their importance. Okay, and these are just to mention, one of the importance is that these waves carry energy to large distances, and they can become unstable, and they generate turbulence. And this is what will the next module be based on, that is instabilities and turbulence. And hence understanding thoroughly the generation and the propagation mechanism of these waves are important, because in the instability sections, instability module will also invoke some of the understanding that we develop in this chapter. So let's get started with internal waves. Now, we know that waves exist in the interfaces between water and air. Okay, and that is what we routinely see in an ocean, in a pond, in a lake. So let's say there is water and there is air. And because of the fact that um, the the densities are different, and the interface disturbance will have to be restored to a horizontal position because of gravity, assuming that this dotted line is the reference level. Any disturbance that we create will generate these waves, and that will take away the energy away from the source of generation. So, and these, and we see those that propagation of energy in form of undulations on the surface. So these are interfacial waves. Okay. Interfacial waves at the air-water interface, for in the most simplest sense. So, uh, extending the analogy of the formation of waves at an interface, we can also see that there is no reason why a wave need not form at the interface of two different fluids of density ρ1 and density ρ2. Okay, given the fact that fluid 1 ρ1, let's say, this is the kind of arrangement that we are making, ρ1 is less than ρ2, for the system to be gravitationally stable, given that gravity acts downwards in all our problems, ρ1 over ρ2 is a stable system. Now we displace it, we make parcels of fluid gravitationally unstable, this any parcel here finds itself in a heavier in an ambient which is lighter than itself, so it has to come down, and any parcel here finds itself in an ambient which is heavier than itself, hence it has to go up. There's a buoyant force and there is a downward force in different locations, and this gives rise to this undulating motion. Hence we have created an analogy of air-water interfacial waves to something in the form of interfacial waves in interfaces of two different fluids, fluid 1 and fluid 2. Okay, so these are, of course, these are also interfacial waves, but now that it is happening with fluids of density rho 1 and rho 2, as with the other case. I mean, this is, of course, this is also just a special case of case 1 is just a special case of case 2. 2 is more general case, whereas case 1 is air water, which we know has a very big density difference, whereas in case 2 we are representing any general situation where rho 1 is less than rho 2. So this is air water interfacial waves is, of course, a subset of interfacial waves that can exist. So in the atmosphere, these kind of interfacial waves can exist when there is warmer air over colder air, or in ocean when there is warm water over colder water. So let's say, I mean, assuming that we can find these distinct layers. This is not always the case. The ocean is all in most of the times mixing, but there are also certain situations when these distinct layers can form. These are examples of interfacial waves. Here we comment that waves can exist in situations where density variation or, in other words, stratification, okay, or in other words, where density, actually the better wording is where density varies or there is a stratification. So this situation can support waves, and we will see their properties. Okay, the waves in a continuously stratified medium, actually the better clarification will is with a continuously stratified medium. Waves in a continuously stratified medium can travel in both horizontal and vertical direction. Please remember, the stratification is quite important. We have learned about the Brunt-Väisälä frequency, and we know that the frequency n is generally represented as minus g by rho naught d rho by tz, and that means if there is a density gradient, this will give rise to this will lead to the existence of a buoyancy frequency, and that is important because the frequencies of these internal waves will be dictated by that ambient stratification, as we'll see very soon. Okay, so as the waves occur in the interior of the fluid, they are called internal waves. this is where we start our discussion on internal waves. The next few lectures will be dedicated to discussion of internal waves. Okay, this is not a barotropic phenomena. This depends on the vertical structure of the fluid. Okay, hence these are baroclinic waves. There are few assumptions that we initially start with to do some analysis, and then we will see that how releasing some of these assumptions lead to different cases, special cases. So first, but just to start in the most simple case, we start with some assumptions. Start with the following assumptions. There is no rotation. The domain is infinite. There is no dissipation. Of course, we have been dealing with non-dissipative system all throughout. Dissipation makes problem difficult. Um, Fluid motions. When I said difficult in the case number C, that is no dissipation, that means it makes the governing differential equations slightly complicated to solve. In point D, fluid motions and wave amplitudes are small. And we might recall what this means, and what is the consequence of this. With amplitudes and motions being small, we can ignore the square of the small terms, and this helps us in linearizing the problem. We retain the partial derivative of the vertical velocity, expecting this to be important, and this means, you can take a moment to think about this amounts to relaxing one certain approximation, and that is the hydrostatic approximation. So we are releasing the hydrostatic approximation. We are assuming that the vertical accelerations might be high enough to be important, or to be of the same order of, or same order of magnitude as the gravitational acceleration. Okay, this, we are relaxing the hydrostatic approximation. Now we decompose the density as follows. So what does this mean? I'll draw a schematic which makes it slightly easier to understand than words. So there is a constant rho bar z. There is a reference value which, without any loss of generality, can be set as 1 or whatever, 0. And this is only a function of z. Only a function of z, and this is a perturbation or a disturbance which can be varying in x, y, z, and t. These are also called fluctuations. But there is a limit on the order um, of these different components that we are decomposing the density into. So rho bar is what you have seen is the variation with density with depth. Rho prime is the fluctuation on top of this. Okay, I'm just drawing some random fluctuation. Now there are, as I said, there are limits on the order of magnitudes of these terms. The rho bar z is much less than the reference density. That is, the background variation is much smaller as compared to a reference density. If you are taking a normalized value of 1 for rho naught, rho bar should be appropriately scaled. But for real life, I mean, with dimensional variables, rho bar, let's say, is the density of water, and the rho bar z should be at least an order or a few orders of magnitude less than rho naught. And this is required for the Boussinesq approximation to be valid. If this is the case, then the Boussinesq approximation is valid. And there is a second constraint on the terms of the above decomposition, is that the rho prime x, y, z, and t, that is the fluctuations, are much smaller than the background variation. And this is what I have drawn here, the fluctuations being smaller in magnitude, and this is needed for linearizing the problem. We can also decompose the pressure as P naught plus P bar Z plus P prime, which is a function of x, y, z, and t. Now, as I told you previously, this is a baroque phenomena, and we cannot invoke the shallow water equations because those are barotropic equations. That is, we have averaged out the vertical variation of the fluid properties. So we need the full governing equations, and going back multiple classes, we know that the governing equations for such a situation are the primitive equations. So using the above decomposition, in primitive equations, and assuming that the terms rho bar is smaller than rho naught and rho prime is smaller than rho bar, our primitive equations are reduced to del u del t equal to minus rho naught del p prime del x. Remember that we don't have rotation, okay, and we are trying to do a simple case as of now, and we will bring back rotation later on. We'll see that rotation introduces an interesting constraint on the frequency of the internal waves, but till the time, let's stick to no rotation case. So these are the momentum equation. This is complemented by, of course, the continuity equation, that is the mass conservation. The fluid is still incompressible, and this is the this is what the incompressibility equation looks like, and conservation of mass looks like. So equation 1, equation 2, equation 3, equation 4, equation 5. So we need a governing equation for density. We have the density evolution equation also. So this equation 5 can also be recast in the form of in the terms of the Brun-Weisler frequency, given that n squared is equal to minus g by rho naught d rho bar by dz if we substitute d rho bar by dz in the form of n squared, we have a certain form, and I'll write it here itself. This is in terms of n squared rho naught by g times w. Okay, so this is the form of the equation. Now we should look at the equations. The coefficients of this whole set of equation are constants, so we can, and given the fact that we have said our boundaries are infinite, this is not bounded in any direction, and this is a quite an interesting assumption. We'll see what happens if it's bounded. Let's assume that it's not bounded, it's infinite in all direction. Then we can seek solutions of exponential form, that is combinations of sines and cosines. So we seek solutions of form e raised to I kxx plus kyy plus kzz minus omega t, where kx, ky, and kz are the wave numbers in the x, y, and z direction, and omega is the frequency of the waves. Now, using these forms in u, v, w, so all of these, like for example, will be, for example, u will be u naught e raised to I this whole term, v equal to v naught e raised to I this whole term. So plug all these things, all these all these expected solutions in these equations. Now we'll get a set of equations which looks like minus I omega u. So we'll get a set of algebraic equations from differential equations. So these are the 4 equations. There is a 5th one, so w, because you have 5 equations, 5 governing equations from the previous slide. So these are the set of equations that we derive using approximate forms of the, using the expected forms of the solutions to the previous previous differential equations. Now this is a homogeneous system. We can rearrange them to form a homogeneous system, and this we can equate the determinant of this set of equations to 0 to get the form of this variable omega. So we are after this variable omega. Okay, so we have the forms of the we have, once we get omega, we'll get the we'll get the forms of the velocity fields, but we are after this term omega um, given the fact that this gives us a quite a bit of information. And we'll see, we can either equate this, the determinant of this whole system, to 0 to get the form of omega, which will give us a dispersion relation. As you recall, the omega is the omega, uh, the relationship or a functional form of omega is the gives us the dispersion relation, because we can then calculate the phase speed, which is omega over k. And if the phase speed depends on the wave number, then it's a dispersive wave. But we can either do this, or there is one more way we can move ahead. What we can do is we can take the time derivative. So this is an alternate method, okay, or this is an alternate method. Take time derivative of the continuity equation, and I'll write down the form. It's nothing but just the time derivative, and then rearranging the derivatives. And because from the x and y momentum equation we know the forms of del u del t, I'm just plugging in their values in the left hand side. This gives me 1 by rho naught horizontal Laplacian of p prime. So delta h is the horizontal Laplacian is equal to the double derivative of w with respect to time and z coordinate. Okay, now using the equation 3 and 5, the original differential equations, we can write this to be okay. So this is one form. Now taking the horizontal Laplacian, you can imagine why I'm taking the horizontal Laplacian, because in the previous case we had horizontal Laplacian appearing. So taking the horizontal Laplacian, so this is an alternate method to solve the above, solve the primitive equations with the approximations that we have in place to show the to find out the dispersion relation for internal waves. So okay, so we're taking the horizontal Laplacian of the above equation. This gives us del square del z del t 1 by rho naught, the horizontal Laplacian of p prime, equal to minus Okay, now this can be rearranged into a single equation in vertical velocity of this form. Remember that in the first term there is no, it's not a horizontal Laplacian, it's a total Laplacian, where this is the horizontal Laplacian. Why is the case? Because we have a horizontal Laplacian on one side and we have a z derivative on the other side, so we can combine the z derivatives and the x and y derivatives in the horizontal Laplacian to combine into a combine the w term, whereas the n squared term will have the w derivative in with respect to only the horizontal Laplacian. That means only the horizontal Laplacian will be acting on the w velocity when it is that in the second term, whereas in the first term we have combined the vertical double derivative with the horizontal Laplacian. So this is a single equation in terms of the vertical velocity, and using solutions of form w equal to w naught e raised to I kxx plus kyy plus kzz minus omega t. This is again the form that we were seeking earlier when we are trying to solve the set of uh, algebraic equations, but this is an alternate method that we have that we are trying to use. Using this kind of a solution, we get a form of omega, and just with some algebra we get that the form of omega is equal to n squared times kx squared plus ky squared by kx squared plus ky squared plus kz squared. This is the dispersion relation for internal waves, and since the numerator is always less than denominator, because all of these are positive terms that are being added, so we have omega always less than equal to n. Frequency of internal waves, so I'll also write this an abbreviation IWS, frequency of internal waves, always less than the local stratification frequency. In this case, actually it's also global because of the fact that we are assuming n to be constant, but we can remove this one, so we can say that frequency of internal waves always less than the stratification frequency. This is a key result for internal waves, and we'll see the implication of this in the next lecture. Thank you.